Hey guys, there's some open spots in the front. If anyone wants to come up front, feel free to. So we'll begin lecture 4 in this course. A few logistics. So I see that most of you have signed up for the paper presentation, but if you haven't yet signed up, then please do sign up because I think the slots get limited as the time goes. You might not get your favorite spot. So we'll talk about that a bit. We'll talk about assignment 2 as well. There is a review session this Friday. So starting this Friday, we'll have review sessions by the TAs. So I think this week it'll be by Urvashi. I think it's 5 to 6. So 5 to 6 on Zoom. So the link will be posted the day on Friday. So just be on the lookout on Discord. And it'll be a summary of the lectures, and also any material connected to the assignment will be covered in the review session, and you can also ask questions after the presentation. So there'll be like a 20-minute presentation by the TA followed by open-ended Q&A. So you can participate in that. So that's covered. Yeah, so we have this winter quarter is usually a short quarter. And also our lectures are on Monday and Wednesday. So the coming Monday is MLK weekend. And then we have a Monday in February, President's Day weekend. So, you know, that gives us one less week. So just to compensate for it, we'll actually have a lecture on Monday, this Monday, on Zoom. It's a holiday. But if you have some other plans, don't worry, it's recorded. But if you can join in, do join in on Zoom. On Monday, because otherwise we'll lag behind on the material with the amount of time we have for this quarter. Okay, so that's covering for the short quarter. We'll have a lecture on Monday, but probably for President's Day weekend we'll not have a lecture, but this weekend, this Monday, we'll have a lecture. Does it sound good? Yeah, so you can join in on Zoom. Also, I've done this before, but if you want to connect one-on-one with me on any pet project that you're thinking about on machine learning or AI or large language models, not related to assignments or office hours kind of questions, you can I'll share some Calendly. I'll share a Calendly link, and you can choose to pick a slot. It's optional. It's not connected to the course, but if you are passionate about something and you want to discuss or brainstorm, I'm happy to do that. So Tuesday 4 to 5, I have 3 slots every week until the end of the quarter. So you can choose to pick it, but it's not connected to the course or any. It's not mandatory. It's based on your interest, and it's optional. Okay. So I'll share a link for the Calendly on the Discord, and if you're interested, you can pick a 20-minute slot and we can chat. Okay. Anything else from your side? Okay, so far so good. All right, so we'll discuss some pointers for paper presentation so that it's more streamlined and we all have a good experience, and you also have a good experience as a presenter. The main idea with this is for you to get in touch with cutting edge papers, like recent papers and the cutting edge research. Also the ability to go deeper into understanding a paper, right? So understanding the high level, the big picture, the nitty-gritties, the connections to what's already, like what is the new contribution of that paper? Why was that paper needed? What did it do? So kind of framing it and understanding it in the context of existing research and existing literature is the goal of this assignment, right? So I think most of you have formed teams of 2, and I see that on the sheet that are now prepped, some of you said, okay, I want to present this paper. Who else wants to join me? I think a few of you are in that boat. Unfortunately, we don't have bandwidth for solo presentations because of the compressed time frame we are in. We can only fit 3 presentations per lecture, and I think it's kind of close to full. So if you can convince the other person to join your team, or you get convinced to join the other person's team so you can present together. That would be the ideal situation. Yeah. So if you're passionate about something, someone else is passionate about something, and you both are solo teams, see if you can join into one team and present. Yeah. That sound good? Anyone looking for a partner? It's a good, maybe you can just raise your hand and others can, so you can talk in the break. So she's looking for a partner. Anyone else? Okay, you're looking for a partner. You're looking for a partner. One more in the back, one here. So 5 folks. So maybe you guys can connect in the break and see if you can team up for this presentation. Yeah? Okay. Make sure to put your name on the spreadsheet so you guys can know who to connect with. Okay. Yeah, so like we said, no more than 3 presentations per class. So the last 15 minutes of every class starting next week, next Wednesday, will be presentations, right? So as we said before, you guys will get to pre-record your presentation so that it's polished and you don't go over time and you feel like you were short on time, or any of those situations that can happen. We'll avoid it by pre-recording your 3-minute presentation. Okay, so you can get to iterate and polish offline before your class so that it's in a good place, and then you can upload it to the drive. We'll share a drive where you can upload, and you can mark it by the date. So let's say you're presenting on Jan 21st, you can say Jan 21st and your name or your team's name, and then we can just pull it up and play it for the class. And so that'll be one component. And unfortunately, we can't do live presentations because we've done it before, and it usually doesn't work that great unless you spend enough time and you're very clear on the time it takes to, we only have 3 minutes. So you want to pack a lot in 3 minutes. We cannot risk a live presentation. So we'll play the pre-recorded video that you upload to the drive in class, and then you'll also have two questions asked in 2 minutes. So you can, maybe we'll have one question from a TA, one from me. So we'll have 2 questions for every team, and you'll be graded on the questions. So the questions are just to test your understanding of the paper. We'll also go through the paper ourselves, so we can see if it won't be a complicated question, but it's just like, hey, do you understand it in a more deeper way? So we'll just assess your understanding. So it's more for that. So I think this one, we said here that we'll have a template for a slide deck. Maybe we'll have some guidelines. We'll see if we want to have a template, or if you want to use your own template, you can. But we'll have some guidelines for what to hit in your presentation because it's just 3 minutes. Okay. So I think so Arnav, you'll share the template on Friday. Yeah. So Arnav will share it by Friday because our first presentation is on Wednesday. So whoever's presenting on Wednesday, you will have the template by Friday, just so that you're prepped well. Okay, and goes without saying, please make sure to understand the paper really well. You can summarize it by ChatGPT if you want, but then it doesn't equate to you understanding the paper. So, so that's why we have the question and answer at the end. Any questions on paper presentation? Okay, all good? Yeah.
Is the link to the sign-up sheet posted on Canvas?
Oh yeah, it's on Canvas. On Canvas, no. Are you on Discord?
On Discord, yeah.
Okay, maybe you can connect to the TA. All our communications are on Discord. So you might be missing out on, if anyone else is not on Discord, please get on Discord, because all our important communications, including sign up links and everything, is posted there. So you'll be missing out if not. So maybe you can contact the TA and, in the break, and then you can get it. Okay. So we have a coding assignment 2 that'll be assigned today, and it'll be due next Friday. So you'll have a little bit longer than a week to get your assignment 2 done. So let's look at a little bit on the assignment 2. It's a multi-class classification problem. So there'll be 5 classes that you're looking for your model to predict. And we are having two models for this assignment. One is GPT-4 Nano as an LLM zero shot or few shot classifier. You don't have to fine tune it. You wouldn't be able to fine tune it because it's closed source anyway, but you can do few shot or whatever. You can do in context learning with GPT-4 Nano. And then we also have a fine tuning of a BERT model. Okay. So for assignment 1, we fine tuned, did we fine tune a regular deep learning model? Okay. So for assignment 1, we fine tuned a feed forward neural network. For assignment 2, you'll fine tune a BERT. So we're already getting into transformers domain, but I think there'll be good amount of boilerplate code, so you don't have to set up all the metrics and loss functions from scratch. So you can fill in the core logic for fine tuning the BERT, and you'll also get to pick your hyperparameters and fine tune at least one of them, so you get some get some hands-on experience with how changing a hyperparameter impacts the accuracy of the model. Okay, so that's something you'll get to do with this assignment. We'll also have some questions on interpreting your results and seeking insights, because that's important. It's not just like training a model and then reporting results. It's like understanding what happened, what didn't happen. So we'll have a couple of subjective questions on interpretation of results and your insights from this exercise. Okay. We also have a Kaggle evaluation. How many of us have done a Kaggle before on any course or any other? Okay, so if not, this will be your first experience. So Kaggle provides an interface where there's a competition typically, and there's a data set on which you submit your model results or predictions, and then your predictions get evaluated by Kaggle on an eval set that's already set up. So you just upload your predictions and it gives you an accuracy number. And based on the accuracy, it'll rank you on the leaderboard. So there'll be a leaderboard of folks who submit the Kaggle. So it's a friendly matchup to see where you stand when you make your submission for the eval set. Okay. So the Kaggle is just a follow-up to your main assignment. So it's not a lot of extra work. You already trained your model. Just make a prediction on the eval set and upload to Kaggle, and you get a leaderboard rank. Okay, so it shouldn't be a lot of extra work, but just to make sure, we give you a couple of extra days. So instead of it being due next Wednesday, it's due next Friday. Okay, does that sound good? Any questions on assignment 2? Okay. Okay, good. So let's move to the lecture component. So we have a lot to cover this lecture. Last lecture we looked at deep learning fundamentals. Today's lecture will finish it, and then we'll move to semantic search. Semantic search is not part of assignment 2, but it's going to be part of mini project 1. So we're kind of covering that component here. It's one of my favorite topics, semantic search. Okay, so last time we stopped at this point where we spoke about how we train a deep neural net, and we said the standard staple diet for training DNNs is stochastic gradient descent. And that actually carries forward with transformers and LLMs, and anywhere you have a loss function, you can say, okay, this model is trained by a loss function. There is going to be a stochastic gradient descent in some flavor, some way, some shape. Okay, so SGD is like a staple engine for optimizing the loss function, and hence also training, and hence also learning. So learning, training, optimization, these are all synonymous as far as SGD is concerned, right? And there's like learning rate schedulers and stuff like Adagrad and Adam and stuff. And how do we compute gradient in a deep neural network? Through backpropagation. So we'll take a look at a little bit of backpropagation. We'll not dive too deep, more high level. So let's look at the impact of learning rate. So there are a few things when we talk about learning, right? So learning, like obviously you have data, train, val, and then test. or eval, whatever, eval, sorry, not eval, val because it's validation, but you also have eval data set. So you can also have eval, let's say your Kaggle is your eval set. An eval set is something you don't have to necessarily be exposed to during your training or test or validation. It's a held out set. So you'll also hear held out. Okay, so obviously you need data for fine tuning or training a model. So the next is you also want to set up your loss function. Like for classification, it's kind of standard. Like we saw binary cross entropy in the last lecture is good for binary classification. And the extension of that is cross entropy for multi-class. So for your assignment 2, you're going from binary cross entropy to cross entropy. Right? So let's say cross entropy. There can be other loss functions as well. When you do contrastive learning, you have a different loss function. Then you have your, I think you have your hyperparameters, let's say hyperparameters. And some of the key hyperparameters are, what are the key hyperparameters? Learning rate. So let's call it LR. What else?
Network size.
Epoch, number of epochs. So what is an epoch? How do you define an epoch?
An epoch, I said network size, but epochs are iterative process of both propagation and back propagation.
Yeah, but what's an epoch? Sorry? Yeah, so one pass through your training data set is one epoch, right? And you can pass through it in different ways. You can pass through the whole thing at once, or you pass it through one mini batch at a time, which is typically the case. So you also set the number of epochs. So 1 epoch, 2 epochs, 3 epochs. That's a hyperparameter. What else? Also, you can say your batch size, mini batch size. Let's say you have 10,000 data points in training. How many of those 10,000 data points are you going to look at one time? How much of the data are you going to learn from in one iteration? So that's the mini batch size. I might have 10,000 data points, and I can update my gradient from all the 10,000, which is like a full gradient descent, full batch gradient descent. But there are some cons to that. So more practically, we look at a mini batch, and maybe you look at a mini batch of size 32 or 128 or 256. So you look at 256 data points at a time, and then you say, what can I learn from this 256 mini batch, right? So that's a hyperparameter. Is it 256? Is it 32? So that's a hyperparameter as well, right? Anything else? Yeah, so these are the typical hyperparameters, but you can also say a meta hyperparameter is your architecture itself. How deep is it if you get to pick the number of layers? So number of layers in a number of layers and number of neurons per layer. Sometimes the architecture is fixed and you just optimize for these three, but sometimes you also get to expand. For example, in assignment 2, we have a BERT model that's already, you're not training, it's pre-trained. But on top of that, you're going to add 1 layer or 2 layers of post fine-tuning so that you can make a classification. So do you add 1 layer or 2 layer? That's again a hyperparameter, right? But the BERT itself, you're not changing. In your assignment 2, you're going to use the BERT architecture as is, but you're going to layer on with either a linear layer or you can have a hidden layer, so two layers. That's a choice that's also a hyperparameter, right? So sometimes this can also be a hyperparameter. Okay. Okay. So now let's look at this one, learning rate. So I'll take a simple example of a quadratic function. Okay, so let's say we have a quadratic function, really simple, and we have to have a starting point. So let's say my starting point is, again, you can assume this is we're showing a one-dimensional space. So here it's x, and then this is the loss, right? So the x doesn't have to be one dimension. It can also look like this. So then this can be x1, and then this is x2, or you can have x3 and x4 and so on. So, but let's say it's to simplify. Let's say it's you just have one feature, right? So we typically start with a particular starting point. So let's say my starting point is here, x0. So my loss at this point is already kind of high. Okay. So if we did gradient descent, it'll say which direction is the negative gradient pointing, right? So what is the gradient at this point? Is it positive or negative? Negative. So for a one-dimensional function or a function of one dimension, it's very simple to compute the gradient. It's just a slope. So if you look at the slope here, this slope is negative. You agree? This is a positive slope, and this is a negative slope. Sorry, I'll just okay. So yeah, so this is a positive slope, this is a negative slope. So right now I picked x0 here. That's my starting point. The slope is negative. So which direction is the negative gradient pointing to? To the right. There's only two directions. For a one-dimensional function, it can either be left or right. It's very simple. If you had a two-dimensional parameter space, then you have many, many options. You have infinitely many directions. But with a one-dimensional feature space, you only have two directions. So because the gradient is negative, the negative gradient points in the positive direction, right? And this is my search space. So if I take a step in the direction of negative gradient, that is gradient descent, right? It's gradient descent because it's a descent, so you take a step in the direction of negative gradient. Gradient ascent is you don't, flip the sign, you just go with the gradient. So here we flip the sign and we take a step in the direction of negative gradient. That's gradient descent. So let's look at a couple of cases. This is illustrative. So let's, yeah, this is a problem. Okay, not too bad. Okay, so let's say I take a small step. Okay, so I take a small step. So I go from x0 to, let's say, x1. So I've gone from here to here, right? My loss is still high. You agree? I went from x0 to x1. So say, okay, then just take large steps. What's the problem? Just take a really large step. Okay, let's take a really large step. Okay, so now instead of going from x0 to x1, I'll go from x0 to something here, x1. Okay, or maybe somewhere here. Let's call this x1. So now look at the loss here at this point. So suddenly my loss has increased even though I went in the right direction. Why is that? I overstepped. So that's what learning rate tells you. It tells you how much you should step. If I understep, I'm not making too much progress. If I overstep, I might actually be increasing the loss. Okay? So instead of going down, I actually went up with overstepping. I want to reduce the loss. I actually want to come to this point. This is my optimal solution. I want to arrive here. Visually, I can see, it's obvious, but this is in one dimension. Beyond two dimensions, you can't even visualize, right? So as an algorithm, I don't know how to visualize. So I am going to rely on small or big or medium sized or correct steps. That's what the learning rate tells us. So if I take a too small a learning rate, I'm making tiny progress, right? From here like that. If I take a too large a learning rate, I am actually increasing my loss function. So there is like learning rate schedulers and standard learning rate policies that kind of, if you follow, you'd be taking a reasonable step, right? And then you arrive at the optimal solution. So this is even for a simple example, you have many edge cases here. With a more complicated example, there's tons of edge cases. Like, it's not just one optimal, you can have multiple optimal points, right, where you can end up in. So the hyperparameter becomes important to make sure, like, you can have the same data and you chose the hyperparameter wrong and you're not getting the right result for some reason. Yeah. So or you change the batch size and then suddenly the same data, like, you got one result and someone else, your colleague or your fellow student, got a different result, and you're wondering, what did I do wrong? It's because of the hyperparameters, right? So that's like kind of a window into learning rate. So typically the vectors are normalized, and then you'll see once you normalize the vectors, your learning rates are typically between -1 to the e to the -4 and e to the -2. So between 10 to the -4 and 10 to the -2, that's kind of like the range that people have figured out. No matter what the problem, no matter what the data, once you normalize the data, this is like a reasonable range. But even within here, you can change the learning rate as you take steps. You can increase, you can decrease, because, you know, as your gradient goes down. So if you notice, once I jump from here to here to here, you see the steps start to become smaller and smaller? Yeah? Is it because the learning rate is becoming smaller? No, I'm not. This is not adaptive. The learning rate is fixed, and yet the steps are smaller. Why? Because the gradient, the magnitude of the gradient is becoming smaller as you get closer to the optimal solution. You see, the gradient here has a higher magnitude than the gradient here. Even though they're both negative, the direction is the same, but the magnitude starts to decrease. So even without changing the learning rate, you'll actually be taking smaller steps. So one idea is, as you keep taking more steps, you know that your gradient is going to diminish, and so you're going to take small steps with the same learning rate. Might be just increase the learning rate a bit because you compensate for it. So that's kind of how learning rate schedulers come into place, is you have adaptive learning rates accounting for the fact that as you get closer to the optimal solution, you're going to be taking smaller steps with diminishing gradients. Yeah. Any questions on this? Like, this is the simplest simplified thing you can have as far as gradients is concerned, because we're looking at a one-dimensional function. Yeah. Okay. So we want to pick the learning rate right, and then if you can add a scheduler as well, like Adam or Adagrad, that can also enhance your progress as you get closer. So these things are anyway automated for us behind the scenes. If you use PyTorch or any of the, your training BERT, some of these things are already optimized behind the scenes. But you'll still get to play around with a couple of hyperparameters in your assignment too, so you can see how the results change. Yeah. Okay. So that's learning rate. Let's look at batch size. So your batch size can, so let's say you have 1 through 1,000 data points, right? So each of this is a data point. Okay. So let's say you have 1,000 data points. My batch size can vary from 1 all the way to 1,000. So if it's 1,000, what is it called? If you said batch size to be 1,000? It's just regular gradient descent. But but people realize that there's a problem with regular gradient descent. Like you use all of the data in every iteration. You learn from every single data point, and you learn iteratively, right? So there's going to be a number of steps. So it's here in this case, it's almost like each epoch, like you take a step and then you cover an epoch. Typically with stochastic gradient descent, you have to take multiple steps before you cover an epoch, right? Here you do a full pass of data in just one step, right? But there's a con here is, what if you cannot load the data in memory, right? Like when you look at training LLMs, we're looking at millions of data points. Can you load millions and maybe even billions of data points in memory? We probably don't have that kind of a memory. So although gradient descent is great, it does work well, it's just not practical, simply not practical at the scale of data at which the models have been training, right? So for large language models, a full batch gradient descent is simply infeasible, right? But that's where stochastic gradient descent comes in with mini batch. Even with stochastic gradient descent, the vanilla version was just the other extreme, right? So this was vanilla SGD. Just pick one data point at a time and see what can you learn from that single data point. But then you'd have to do 1,000 steps to cover an epoch. There was another disadvantage of just using one data point at a time. Any guesses on what that was? Yeah?
Really noisy.
It's really noisy. So you can use stochastic gradient descent with one data point or a mini batch of 32 or 120 data points. But one data point can point this way, the other data point points that way, and then there's too much of noise. But when you take a mini batch, there's an averaging effect that happens. And we know that when we deal with averages of data, there is a kind of smoothness and continuity to the progression of optimizing the loss function, right? So just to go a little bit deeper into this. So people have seen these kind of curves, right? So you have a loss function, and then let's say this is epochs. So 1 epoch, 2 epoch, 3 epoch, so on. Okay, so what people have observed is that if you use the vanilla gradient descent, you might start here somewhere, and then your loss kind of oscillates quite a bit. Okay, and then if you use mini batch, so this is vanilla SGD, where your batch size equals 1. And then you have your mini batch, it could actually oscillate as well, but not as much, right? And it might actually even perform better on the loss. Okay, and then you have your full gradient descent, which might even do even better, but it's just not practical. So if you use the full batch, say this is batch size equals 1,000, and then this is equals, let's say, 128. So there's too much noise here, and that's why this is out of favor. People don't set batch size equals 1 anymore for noise reasons and also accuracy. So typically you're somewhere in between 128, 256. So with a lot of experiments, people have kind of honed in on a mini batch size somewhere between 32 and 256. That seems to work no matter how big your data is. You might have millions of data points, you might have billions of data points, but you can still work with a batch size of 128 or 256 and get reasonable results. Might go until 1024, but that's amazing, right? So across a wide variety of data and models that you want to train, there's some kind of constant settings for these hyperparameters that really work well. That's kind of the learnings from a lot of research. Okay. So that's a bit about batch size. Any questions on learning rate, batch size? Okay. Let's do an in-class exercise. So you can open up the canvas. Hoffe is here. Hoffe, you set it up, right? Okay, yeah. Yeah, you said you published it, yeah. So you can go to the in-class exercise and look at this question. So there is a loss function. Your parameter is theta. and there are d such parameters. So theta is a vector, and theta I represents the ith dimension of that vector. So essentially, you have d parameters. So the question is, what is the dimension of the gradient with a full batch size and a batch size of 8? So you can assume that d is greater than 8. Okay. We take like 30 seconds or 1 minute to look at this.
Karthik, you had a question on Zoom.
Okay, we'll answer that. So we finished in class exercise 2. Let's move on to forward and backward propagation. So forward propagation is very simple. It's just evaluating the loss function, right? So just move or getting the predictions is the forward pass. Sorry, not evaluating the loss, but getting the predictions is the forward pass. So if you go from input to output, that's forward propagation. And this is equivalent to getting predictions, equivalent to inference. So when we say inference, okay, let's do inference, we're just doing a forward pass. And we might do it in a more efficient way. We might quantize parameters. We might use float 16, float 8, int 8, whatever. So we might use different quantizations, but it's essentially a forward pass. Okay, and that's inference. Backward propagation is basically the simplest way of thinking about backward propagation is backprop equals computing gradient. That's it. So backprop equals computing gradient. Backprop equals learning from the data, because you're backpropagating the information or the corrections that you need to make. You did a forward pass and you said, okay, there's something off. The loss function says, okay, I'm still high error. So let's propagate the information back to the parameters and update them. That's backprop. But essentially, it's computing the gradient. We use the composition rules, because from one layer to the other, there's a composition. The output is a composition of all the layers from the input. So we just use rules of composition to backprop. And that's just computing gradient. I'll skip this slide because it's, but you can take a look. Yeah, so it can be thought as a flow of information from the error in the output down to the weights. So update the weights so we don't make this error next time around. So that's how you learn. How do we learn as humans? We learn when we make mistakes and say, I'm not going to make that mistake again. I fell down, I'm not going to fall again. So I learn, I make some changes. So when you see an error in the loss, you propagate that back and say, I want to learn from this error so that I don't have this error again. That's essentially what backprop is doing. Okay, so let's do one more in-class exercise. So I'll just put a caveat here so you can answer this better. What powers the learning component when fine-tuning the parameters of an LLM in post-training? And this can be any kind of post-training. It can be supervised fine-tuning or, well, I guess we have not talked about post-training so much, but make your best guess. It can be any kind of post-training. Doesn't have to be, it can be supervised fine-tuning or LoRa fine-tuning or instruct fine-tuning. And essentially we're saying which components are really essential for learning, right? So which of these are really essential for learning in post-training? So you can have more than one correct answer. So you can select all that applies. Um,
Big, medium, small,
let's say medium to big.
and GPUs.
Yeah, as well.
Data.
Sorry,
Data. The first one.
first one. Yeah. Okay, do respond to the in-class exercise and we'll talk about it. Everyone got to respond? Yeah. So definitely data, right? If you didn't have good high quality data, you would not be able to do, it'll not be able to power the learning. You can have the best hyperparameters and everything sorted, but your data is not off, you're not going to be able to do good learning. So definitely data. And SGD for sure. I mean, for some reason you're not using SGD, there is something off with your learning. Okay, we spoke about it. GPUs, yes, like someone said, if you have enough data and enough number of parameters, so we're looking at mid to large scale training, GPUs are indispensable. You simply have to use GPUs. Reinforcement learning powers certain parts of fine tuning, but not all. You don't need to use reinforcement learning for supervised fine tuning. You don't need to use it for instruct fine tuning, but you need to use it at the last stage, very last stage. So reinforcement learning is optional, depends on what you're doing. Okay. All right. Yeah, so this is another, I think we spoke about minima. So I think it's a better depiction of a surface of a loss function as a function of two dimensions, right? So we're looking at x1, let's say, and x2. So yeah, this is one local minima and this is another local minima. I'll skip the good and bad local minima. I think that's a little bit extra concepts for this class. Yeah, so hyperparameters in deep learning, we spoke about this. Learning rate, number of hidden layers, number of neurons per hidden layer. Type of nonlinear activation function used. Yeah, this can also be something you can, if you're getting to change or pick, then that's also a hyperparameter in some sense. And then batch size. Okay. Hyperparameter tuning methods. Yeah, we'll not be looking at it in this class, but we typically tune hyperparameters on which data set? Train, validation, or test, or eval? Not train. Validation. So validation is the data set where you say, I've already done training on my main parameters, but the training actually depends on the hyperparameters, because once I fix it, I train. So if I want to change the hyper, I actually test it on validation. So you fix a hyperparameter, you train the actual parameters, and then you evaluate on the validation set, and you repeat that process with your different configurations of hyperparameters and see which one works best. Which setting of hyperparameters gives you a good accuracy is tested on the validation set. Okay. And then you use those fine-tuned hyperparameters to actually evaluate on the test set. And that's the accuracy that you report, or the eval set, right? Okay. So hyperparameters fine-tuned on val set.
Can I just shuffle the training data set and do the hyperparameter tuning?
Yeah, you can do that, cross-validation, right? But you always, even for cross-validation, you fix the training, you fix the validation, and you only evaluate on validation. You don't evaluate. Whenever you fix it, you still evaluate on the validation. But you can shuffle it and average it out. That's called cross-validation. It's more time-consuming, but you can.
Shuffle on the training part or shuffle both the validation and training?
Yeah, you basically break up the whole data into train and validation and test, and then you shuffle that whole breakup. You do that 10 times, like you can do it 5 times or 10 times. And then you train on train, validate on validate, get the accuracy, average it across all your shuffles, and then see which configuration of hyperparameters gives you the best validation accuracy. And then you say, this is my final hyperparameter that I'm going to go with. Then you use that to evaluate on the test set and then report results. Okay. train, and then results reported on test or eval held out set. Okay. So train, validation, test, eval, or held out set. So these are. Okay. Any questions on this? We're not spending a lot of time here, but you'll be looking at hyperparameters. I think at least one of them will get to fine tune in your assignment 2, and you can see how the results change. Okay. Yeah, I think this is a slide that, I mean, this is a nice slide. I like it because it kind of shows you the evolution of neural networks. Like we looked at perceptron, we looked at feed forward, and then, sorry. Yeah, we looked at feed forward, and then this is a DNN, deep neural network, or deep feed forward neural network. We looked at RNN briefly, a history of deep learning. We looked at LSTMs, and then GRU is connected to this. We're not looking at autoencoder and these guys as much. We will be looking at it actually. We'll be looking at it when we talk about stable diffusion. So when you look at LVMs, large vision models, when you want to generate an image or video from text, you're using stable diffusion architecture, which is based on an autoencoder, right? So we'll cover autoencoder at that point. So then there's other ones that, then we also spoke about CNN, and then there's deep CNN. We probably won't talk about GANs, although it's an important topic. Yeah. I think this is something like this is in stable diffusion. So anyway, there's a bunch of different architectures, but we don't have to cover everything as a background. Okay, so we'll stop here for this part of the lecture. We'll take a 5-minute break, and then we'll go to the next part of the lecture.